Right. From Paris-Est, who will talk about polynomial.
No.
Collaborators and friends, Ramon Anton and François Vigneron. And we were actually working on something else, doing the Newton method around the Mandelbrot set. And at some point we realized we can improve another algorithm, which is much more basic than the Newton method. It's just plain polynomial evaluation. And then I followed the nice talks before me, and I put the title of my talk and the title of the conference on the same slide. And I realized not only is the furthest away work that I've done from the topic, but also the furthest away talk from the topic of the conference by far. So I needed a strong justification for this. And the first lazy thought was to blame the organizers. But actually, I'm very grateful to them for the opportunity to be here in front of you and for helping me to get to this remote and timeless place, despite my wandering orbit in Poznan last Sunday. So that was not an option. I would say if you try to use the Newton method to split a polynomial, this will apply very nicely. And whatever improvement you do to the Newton method, this will be additive. So it's transparent. You just evaluate the polynomial and the derivative faster, and whatever you do better with the Newton method, you can combine the two. But still, weak justification. So minor epiphany, I took a closer look at the full title of the conference, and then I became happy again that I can present this work. Let me go back in time a little bit and use this very nice advertising by Laplace of logarithms, which can double our life, well, astronomers. The idea was to get the same result with so much less work. And what we do today, we replace the slide rule by the microprocessors. And even though they are very, very quick, we still want to optimize any kind of algorithm that we use on them. And if we talk about algorithms with numbers, we have to, well, I have to tell you a little bit how numbers are written in the computer memory. So we have, they like much more base 2 than base 10. They don't have 10 fingers. So you will have an exponent of a number, a sign, and then you will have some bits, which are the equivalent of the digits, but in base 2, which means that if you want some kind of approximation of the logarithm of the absolute value of the number, it's already there. It's already written there. You don't even have to compute the logarithm of the number. You already have it, the logarithm in base 2. And then what does it look on the real line? Well, if you only have a fixed precision, a number of bits or digits that you want to use, when you get closer to 0, because you multiply by this, the gaps will go smaller and smaller. And when you go close to infinity, they're larger and larger. So it's only in logarithmic scale that this is kind of uniform representation, but in Euclidean distance, well, you have this. You have very precise numbers, let's say near 0, and huge gaps near infinity. And then, of course, we want to add and multiply numbers. And we can see that numbers are kind of polynomials. And as we have much more difficulty of multiplying numbers, the computer does the same than adding numbers. So if we can spare one multiplication, so if we divide by to the size of our numbers. We put half of the digits here and half of the digits there, because if we put a power of z, means that, well, z is 1/2. It means the second half of digits. So we cut it in two, the two numbers, and we want to multiply. It looks bizarre. In practice, we will never do that. But if you see, you have one multiplication here, one here, and one here, because you already compute those two. So you split your problem in half. And instead of doing 4 multiplications, instead of getting to a time of computation like a square, you actually gain, every time you divide by 2, you do only 3 multiplications instead of 2, and then you do this recursively, and you can have algorithms much better than the standard one of multiplication of numbers. And the limit of this is p log p almost, with a rather large constant, but not universal, meaning that maybe starting at 5,000 to 10,000 digits in base 10, this algorithm becomes quicker. If you have hardware numbers, those that are already built in the processor, this is like 3 processor cycles, and we have computers with about 3 gigahertz. So it means you can do 1 billion multiplications or any kind of operation per second. Yes?
Lower bound for the
No, I think this is the
Question. Not only yours, but in general. I've seen one paper once where this was replaced by log star of p, meaning how many times you have to take log of log of log of log to yes. But in this case, the constant here is astronomical. So it's an astronomical algorithm. You will never apply it. It will be maybe 10 to the 200. So you never want to do this in practice. But of course, the question, how low can you go? I have no idea, and this would be an absolute nice project to prove a lower bound. There is a lower bound if you don't have the numbers, the complete numbers at the start of the algorithm. If you only get one digit, one more digit at a time, and you have to produce the intermediary results, then I think there is a bound p log p. But if you have the numbers, I think it's not no. So, of course, this little trick applies also if you want to multiply polynomials, not only numbers, because, well, this is already polynomial. But I don't think I have to advertise polynomials for you. You know they are used everywhere. We like them. We spend a lot of time with them. But actually, I will stop for an advertising break about our work on the Mandelbrot set. So we have split those polynomials that give the critical orbit to find the centers of hyperbolic components and some Mihalache-Thurston parameters. So we have all the centers up to period 41. We have 1 trillion centers of the Mandelbrot set, and this is a number that it's hard to imagine until you have to take care of a set of that size. We have those numbers on hard drives. It takes weeks just to move them from one place to the other, and we compressed them the most we could. So this project took maybe just a little bit less than 1 century of core computing on this supercomputer. The irony is that we cannot use this algorithm here of faster evaluation because it's by composition. We already evaluate the polynomials in logarithm time, so you never explicit those polynomials. So we cannot use it there. But anyway, if you ever need for any kind of experiment or artistic purpose, those roots, we have plenty of them and we sell them very cheaply. So
Which so does the root give you some clear estimate on this possible maximal size of a queer component?
you only find those And actually, we exploit this already.
Dirk Fleischer. Because once you have the hyperbolic component, you can write the series of the Riemann map, and you can compute very nicely the area. And we have so many of them. And we have a new algorithm that will find even larger periods, but those that are physically large. So we are trying to bound the area of the Mandelbrot set from below and from above, and see what about the boundary and so on. But this is another story that, but the queer components is, yeah, I don't see how we would get going from the hyperbolic set.
You said that it was until 41.
Yes, because you have
Usually the Newton method, well, at least the standard Newton method. There is a paper in 2001 by John Hubbard, Dirk Fleischer, and Shatterhand, yes, where they give you a receipt from solving all polynomials. If you go on one circle or several circles, you are sure to hit, I mean, those orbits of the Newton method to find all the roots. The problem is, the higher the degree, the thinner the channels. And then in the channels, you do about degree of the polynomial steps, and you have degree of the polynomial root, so it's already quadratic. And on top of that, you have to multiply by the time to evaluate your polynomial. Okay, it's logarithmic. Their set is also logarithmic, so if you do that, if you want to have a quadratic algorithm, 2 to the 41, there's no way. So we have found a way. Unfortunately, it's not general for all polynomials. That is time basically linear in the degree of the polynomial. So instead of starting on these large circles, you will start on a level line, which will refine the mesh of starting points exactly where is needed, where you have more roots of the polynomial, and you are much closer, and you don't spend your time going through this disk all of your life just to get some roots in the end. You already start very close to the roots, and this basically constant time iterates to get each root. So that's why it was possible, not only because it's a huge computer, but then we had the computer, so why not? So, yeah. Okay, going back to the usual program. So now, how do people evaluate polynomials in general? Well, if it's just a monomial, we know we can do in logarithm time, of course. This M of P that I had on the previous slide is just the time to multiply two numbers of imprecision P. And here I will do another advertising for something that we did not do, a library which is called MPFR of numbers, which is fully optimized in the sense that you give it two numbers and it will automatically choose the best algorithm for your numbers and for your computer, and guarantees correct rounding by the what you say, so you can do interval arithmetics and numerically prove stuff. So I should have written it somewhere, but I will write it on the blackboard. So MPFR, I don't remember what does it come from, but if you ever want to do computations that are quick, high precision, and guaranteed results, this is it. And guarantees, even for transcendental functions, correct rounding up to the last bit. So it's yeah, it's the best you can have today. Well, so this number here that appears here, just how much time you spend to multiply two numbers, which depends on many things and the algorithm that you choose. Then is the standard Turner method, which compared to just obtaining the powers of z and multiplying by number doing the sum, you gain a factor of 2 because you only do one multiplication and you get both the powers of z and the coefficients. And actually there is a theorem that says that if you are given one polynomial and 1 point, you cannot do better than this, because you just have to look at all coefficients, compute. There's no way to do better if it's one polynomial, 1 point. So why do I tell you about a faster method? Because our method will be to evaluate the same polynomial several times in many points, which is exactly what you need for Newton method, for example. Then more involved schemes is that if you want to evaluate some polynomial on roots of unity, then you can use the symmetries and do much better than, well, you evaluate in d points, so instead of having d square, you have d log d. But of course, this is quite particular. It's very useful in many cases, but not for the Newton method, for example. There is another method which is quite nice, some algebraic construction, but unfortunately, you have to do polynomial division, which is not necessarily very slow if you do it in a smart way, but some problems are, some polynomials have intrinsic instabilities, which forces them, the people who invented this, to have an intermediary precision, which may be much higher than your initial precision. And you have to work with all the points in the same time. So you have to know them in advance, which is not true for a trajectory of the Newton method, for example, but also it takes quite a lot of memory. So if you ever imagine D to be like 1 billion, already D square for the memory of a computer is probably not for the next 20 years. But it's a very interesting method. It works very well for lower degrees. And here, if you have the same number of points as the degree, you get rid of this M of P somehow. So despite the fact that the precision increases, you still have some definite gain. Okay, so this is what it's usually done. Now I want to go back to primary school and tell you how to add numbers, but in a way that they never teach us, the lazy way. What does it mean? If you're in fixed precision, your numbers are given only with, let's say, 4 digits. And your result only has space for 4 digits. So if you know that the exponent is a bit larger than the precision, then if you do the addition or subtraction or whatever, and then you do the rounding because you can only keep 4, well, it's the same number. You can ignore the other. You don't do anything. So this is lazy addition. You just look at the exponents, which are already there. If they're far away, you can throw away many things. Okay, so what can we do with this? Well, the naive way would be, well, you have a list of numbers and you sort them and you start adding. But of course, this is very, very slow. Just to sort the numbers is D log D. By the way, if anyone knows a better algorithm to sort D numbers faster than D log D, probably for that, we can show it's not possible.
I think there's a proof.
Anyway, it's slower than Herner method. Of course, there are, these problems. If you have a very long list of numbers or infinite sequence, then of course, how can you guarantee that the sum of the tail is small and so on? But we can still do something with it for the polynomials. Let's look at the graph of the logarithm, the scale of the coefficients of our polynomial. Because if we only have like 6 digits, this is just some kind of one horizontal strip here. So you look at the highest coefficients, and if you go a little bit below, you can ignore everything that is below. If the degree is very large, you may have to add, you have to add log of d to the thickness of your strip, because you have to bound the largest sum of whatever you ignore. So, as I said, you will take only the highest scales this is already in logarithm scale. You can ignore everything else, including those that are here. So the first idea is just you build a concave cover. Well, usually people like to say convex cover, but well, that's the way. You will forgive me if I say concave cover is just minus convex cover of the scales of the coefficients. And in the very easy case, when the modulus of z is 1, well, modulus of each monomial is the same as modulus of the coefficient, and you just know what you can ignore. And this concave cover has two advantages. You can, once you have it, you can find very quickly where is the peak, because it's binary search. For example, the derivative is decreasing, so we will search for derivative 0 or negative on one side, positive on the other. So it's very quick to localize this. And then it's also very quick to localize the intersection here. It's another binary search. This is done in log d time. So if you somehow already know this cover, you will know very quickly up to where you have to sum. So here is the degree. Yeah, so this is log of a6 or a6z to the 6. So if you have this red line, you can ignore everything that is to the left. So you can do a Herner method from degree 5 to degree 9. And in this fixed precision of your result that you can read on the vertical here, you can safely ignore everything else. So you do a much shorter evaluation than the full evaluation. Now, what happens in the general case when the modulus is not 1? Well, it turns out that we can compute very easily the scale of monomials because it's a power and you take the logarithm. So you just add a linear function to your concave graph and it stays concave. So now, okay, if lambda here will be, so modulus of z is smaller than 1, lambda is negative, your previous graph, which had high values for high degrees, now high degrees have smaller values, but now you have some other problem and maybe even longer. I mean, the span of powers that you have to evaluate may be longer than before. So this looks nice, but is there any guarantee that repeating this procedure for all z will give you something better than Herner? And actually, yes. Exactly those ideas help us prove the following algorithm. So we do this construction of the concave cover in d log d time, but which does not depend on the precision, because if you remember, the numbers have the scale already written somewhere, and then the bits, the digits, differently. So you already have the scales. You don't care about how precise they are. So in practice, this becomes quite quick, even though there is a log d there. But anyway, you do it only once. Then you can spread it to several computers, and all subsequent evaluations can be are embarrassingly parallel, so it means that you don't have to do anything. What about the average complexity on your favorite set, maybe the unit disk or the Riemann sphere or the real numbers? It turns out that instead of having linear time, like d times m of p, you have d to 1/2. Well, there is the precision here, but the precision is considered fixed. You work in 100 digits, and your degree is large. So at some point, this is just basically constant. Well, logarithm is constant on the computer. You never see a logarithm going to infinity when you do something in practice. And if at some point, so this is the average time. Of course, from time to time, you will have to do the whole Herner scheme. But average time, it's at most this. What happens if there is one modulus of z which is particularly bad, meaning that you have to do like a full Herner? then actually your average time decreases quite a lot. Instead of being square root of d is just log square of d. Well, log square or log d is constant on the computer. And you don't lose anything in precision by this consideration that all other monomials are very, very small in modulus. And because you know the scales that you expect from the coefficients and the powers of z, you can look at the scale of the result and you know exactly when there are cancellations, because cancellations tell you that the precision of your result is not precise up to p bits. You have lost maybe 3/4 of the bits. You only have 1/4 of the result, which is correct. Everything else is garbage because it comes from some error terms, and the real, I mean, the important terms simply get canceled close to zero. So everything here comes like free. And then how does it work in practice? Well, here is the degree of the polynomial in logarithm scale. And here is the gain speed, the speed factor that you gain compared to the Herner method. So this is the general algorithm. And the other one is when you have once the bad case of Herner, then it becomes much faster. And this is for numbers which are very quick in the processor, so not much precision, which is not such an advantageous for our algorithm because we avoid many multiplications in high precision. How does it work with different precision? Here is the name of this library that we use. Here we have log graph, and we see this square root of d appearing like the slope of those complexities when the degree increases. So yeah, we have implemented this this algorithm. So the all the source files are available in open source and everything. If anyone is interested to test or to use them. Here is a statistic about precision loss. So we compare our method to the Herner method and to the real result, to the actual result. And it looks like in practice we lose a little bit more than what we gain. So it's not perfectly random, but we lose half a bit, half of a digit in base 2 in more or less the worst case. But it seems that we never lose 1 bit, yeah, compared to the Herner method, because from time to time there will be cancellations, and you cannot have a precise result no matter. I mean, you would have to have Z more precise, coefficients more precise, but this is another algorithm. So, and now a surprise. There is a theorem that says you cannot do better than linear time for one polynomial and one point. But actually, statistically, we can do better because this evaluation step in the beginning, and of course, this is probabilistic. I mean, this is in average. In average, you put one polynomial and one point, and you look how much time it takes. So when you use high precision numbers, like what, 200 and something bits means about, it's less than 100 digits, right? Because 2 to the power 3 is less than 10. So we have a gain factor of 1.5 or something with one polynomial and 1 point. Of course, it does not contradict the theorem because this should be in every point and it's not finite precision and so on. But in practice, we do a little bit better. We almost do the impossible. Yeah. So what about the proof? How much time do I have? So a few words about the proof. You remember that we want to sum only those terms in the expression of the polynomials which have high scale. And we can renormalize, I mean, we take the degree and we divide everything by d. We put this map on the interval 0, 1. So we simply have a concave map on the interval 0, 1. And we look at the longest segment with a given slope, tangent of theta. And then we project this so it will be cos theta, because when we project, we get exactly the span of indices that we have to consider in our sum. And when you renormalize to 0, 1, it's exactly the ratio of terms that you have to evaluate. So then what do you need to prove to have average complexity of your algorithm? You just have to take the average of this length of this projection. So yeah, you prove an inequality for all concave maps of the interval. If you integrate this thing, it behaves just like the square root of delta with a very precise, I mean, low constant. It's not an astronomical algorithm. It's not 10 to the 100. And there are examples which show that this constant is not very far from the optimal. And then if you want to change the measure with respect to which you do the average, because you can do on the unit disk and so on, you can play with the weight here, and that's another example, and it will behave more or less the same. So how now, finally, a little bit of mathematics. How do we prove this, this bound? Well, let's go back to this concave map. We add this linear map. So our segment, which was slope tangent of theta, which here is tau, becomes horizontal. And we want to estimate the distance from the left point to the right point, the average of this distance. And basic calculus says that, well, from here to the middle, we gained delta on the vertical, right? Because that was the strip, that is the height of the strip we are using. So you just have to integrate the derivative of this and you get delta. So from here, knowing that delta is here, we want to get this distance from, let's say, this kind of middle to the left and the middle to the right. And then we take the sum and do the average. And this will give us the inequality. So maybe I will simply write this, this integral just to have it there. So it's from the left point to the middle point of f prime of t minus tau. This is delta. And if now instead of drawing the graph of f, I draw the graph of f prime, which may be discontinuous, but I can complete it to a curve. What does it mean? If I look here at height tau, because I take derivative minus this, right? So this is what I integrate. So I integrate from here the derivative. So of course is the area under the graph. And that's how I get this coordinate, the left coordinate, such that the area here, it's exactly delta. So now I have a curve here, which is decreasing in tau, meaning that when I go up, the curve goes left. And I do the same on the other side, because now we can go from the middle point to the right point. And we have this geometric information that we have those two curves, which are given by the left point and the right point. And what we are interested in is the average width, horizontal width of this channel. But we have this geometric information that area here is delta and area here is delta, which we cannot use in this form. But I will redraw this picture. Let me skip this for a moment. So if I take a point on this left curve, if I go to the graph of f prime, so even higher, I will have area delta here. Then I go on the diagonal of some square until I hit the other curve. Now going from this curve to the graph of f prime down to here, I have area delta. And no matter what the configuration is, I mean, there are only 4 configurations compared to the other 2 corners of the square, I have that the area of this square going from one curve to the other, it's at most 2 delta. So now I have a bound on the diagonal, which, if my powers of 2 are correct, is 2 square root of delta. And we are very close because this is a little bit what we are searching for. Now, this strip is infinite, but when we want to have this integral, so this length of delta theta goes from minus pi over 2, pi over 2. This is the same as the integral. Let me write an extra term. So it's the same variable as here, pi over 2 of the right point of tangent of theta minus the left point of tangent of theta. And some change of variables, which is an easy exercise, gives you the last formula there. Oh, sorry. Here, which means that when you go in your channel high enough with tau or low enough, actually this, you can easily bound this. Let me write the last one too. XR of tau x left So now we are almost done because we have this diagonal of the square where we have this estimate square root of delta, and we just have to turn it 45 degrees. On some interval here, we don't care about this factor that will help us near infinity because it's not needed. But starting at some point, which is explicit, not only we have the height, which is at most 2 square root of delta, but we also have this factor that will make it integrable. And this is basically the proof of the inequality. Do I still have time or? 10 minutes. Would you like to stop a little bit earlier to go to lunch, or because the last that was the inequality. I could bore you a little bit how you construct the convex cover of a set to have this concave cover of the function, but this actually we are not working usually in this domain. We have heard this is completely standard, so this is done in D log D, and maybe I stop here. Thank you.
Questions? Okay. Now, do you think this will utilizing your method would be an improvement to computing the transcendental map? So take a transcendental approximated by polynomials and use your method to for the polynomials. Do you think?
Some domain you have a good approximation by the polynomial, then you do it for the polynomial. You get the roots, and then how do the roots of a polynomial move when you move the parameters? Of course, it's not always easy, and how your error from the polynomial to the map influences this, you have to be careful, but I think yes. And actually it's compatible, I didn't say with the Newton method, because when you do the Newton method, usually the modulus of your Z, you come from some point and it moves. So you actually see the average. You cannot be in the worst annulus of Z where the algorithm is slow. You go through different modulus and it will get to the good average, you know? And you don't even have to write the derivative of the polynomial explicit, because if you have the concave cover, you can modify it a little bit to have the concave cover of the derivative. So there are gains to be made there. But it's particularly compatible with the Newton method. So.
Actually managed to publish a theorem with phrasing embarrassingly parallel.
Actually, my collaborator who insists on this, because he did some numerical analysis, and they say this is that's the term you have to use to convey this thing. I'm a bit against, but yeah, we'll see. We'll see. Our paper is submitted in October 2022. I hope it's not this problem that we don't have an answer for almost 2 years. So.
I have a question. It's correctly that this method works well for high degree polynomials of order 100 or so?
It works, but your gains may not be so. Let's say.
Yeah, maybe more than 100. When you are at 100, actually you're a little bit slower.
Wait, are you finished?
Already at 1,000, bigger than
Improve the precision instead of only for 300 bits, say 3,000 bits. Do you think it will be better in for 100 degrees?
It should not grow in degree.
Because otherwise, if the precision is the degree, then you have d square here, and which is Herner, and you also have something extra. So it should be in a way fixed. Even if it's high, it should be fixed, and then degree to be much higher. Otherwise, there's no point to use it.
So in principle, you could you use it for quadratic polynomial just by taking long key derivatives, no?
Unfortunately, this algorithm
Doesn't serve, because for quadratic polynomials, when you do this PN to find the hyperbolic centers, how do you compute? You do square log of degree times, which is much better than square root of the degree. So it's ironic that what we have found when doing the Newton method for the Mandelbrot set is not useful for that, but it's useful for maybe other things, but not the Mandelbrot set or Julia sets, or low degree Julia sets. Now, if you want to have the Julia set of polynomial of degree 1 million, then I think it will do very well.
Other questions? No? Okay.
Yeah,